Tonight, we're going to go somewhere no telescope has ever reached. Past the last galaxy we can see. Past the edge of everything mapped, everything measured, everything confirmed. And what's there isn't empty space. It isn't nothing. What's there might be more universe than everything we've ever observed, multiplied by a number so large our mathematics barely holds together when it tries to describe it. By the end of tonight, you're going to understand not just what lies beyond the observable universe, but why the question itself might be the most important one our species has ever asked. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with a wall, not a physical wall. Not a boundary you could touch or approach or photograph, but a wall nonetheless. It surrounds us in every direction, up, down, left, right, forward, backward. A perfect sphere with us at the center, extending roughly 46 billion light-years in every direction. Beyond that sphere, our instruments go silent, not because nothing is there, but because the light from beyond that distance hasn't had time to reach us yet. The universe is 13.8 billion years old. Light travels at roughly 300,000 kilometers per second. That's the fastest anything can move. And even at that speed, there are regions of the universe whose light has simply not had enough time to get here. They emitted light. That light is crossing space right now. But it won't arrive for billions, or hundreds of billions, or trillions of years. We are sitting inside a bubble defined not by any physical feature of the cosmos, but by the age of the cosmos itself. And everything we know, every galaxy catalogued, every star imaged, every cosmic structure mapped, everything is inside that bubble. This is the observable universe. And it's important to understand something clearly from the start. The boundary of the observable universe is not the edge of the universe. It's the edge of our view. These are two completely different things. One is a property of light. The other would be a property of space itself. And right now, based on everything physics tells us, there is no reason to believe space ends at our cosmic horizon. Every reason, in fact, to believe it continues. The question is how far, and what's out there when it does. To understand what lies beyond, you first need to understand what the observable universe actually is, because it's stranger than most people realize. Right now, we can detect galaxies whose light was emitted when the universe was only a few 100 million years old. The most distant confirmed objects are over 13 billion light-years away in terms of light travel time. But here's where it gets strange. Because the universe has been expanding this whole time, those galaxies are not where they appear to be. The galaxy that sent us light 13 billion years ago has been moving away from us the entire time that light was traveling. By the time the light reached us, the galaxy had moved. It's now roughly 46 billion light-years away. Space has been stretching, and not just a little. The expansion of the universe means that the same galaxy we observe is now far beyond the position suggested by how long its light took to arrive. This is one of the first genuinely counterintuitive things about the observable universe. You'd think the edge of what we can see would be 13.8 billion light-years away, because the universe is 13.8 billion years old, and light can travel 1 light-year per year. But that ignores expansion. The universe was smaller when that light was emitted. As the light crossed space, space itself stretched. Both things happened simultaneously. The photon moved. The space it was moving through expanded. The result is that the photon arrived having effectively crossed a much larger distance than its travel time alone would suggest. Take a photon emitted by a galaxy when the universe was about 1 billion years old. At the moment of emission, that galaxy was perhaps a few billion light years from us in the coordinates of that moment. But by the time the photon arrived, the space it had crossed had stretched enormously. The photon still only traveled at 300,000 kilometers per second. But the space it was traveling through kept expanding as it moved. So the photon arrived after crossing what was effectively a much larger distance. And the galaxy itself is now about 46 billion light-years away, because space continued to expand while the photon was in transit. We are seeing that galaxy as it was, not as it is. Every single object we observe in the sky is a piece of the past. The further away it is, the further back in time we're seeing. Nearby stars we see as they were a few years ago. The Andromeda Galaxy, the closest large galaxy to our own, we see as it was 2.5 million years ago. The most distant galaxies we've imaged with the James Webb Space Telescope we see as they were over 13 billion years ago. The observable universe is a machine for looking backward through time. And the cosmic microwave background, the furthest thing we can see, shows us the universe as it was 380,000 years after it began. The observable universe contains roughly 2 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. And this entire staggering inventory is just the portion of the cosmos we happen to be able to see from where we sit in space and time. If you could travel outward from Earth right now, in any direction, and if you could somehow travel at arbitrarily high speed, you would pass through everything we know, past the Milky Way, past the local group of galaxies, past the Virgo supercluster, past Laniakea, the enormous supercluster of which we are a part, spanning roughly 500 million light-years, past the cosmic web of filaments and voids that forms the large-scale structure of everything observable. And then you would reach the edge of what our telescopes have ever seen. And you would keep going, because the universe doesn't care about the limits of our instruments. The current best understanding of cosmology says the universe extends far beyond what we can observe. How far beyond is one of the great open questions in physics. 3 possibilities are on the table. The universe could be infinite. It could be finite but closed, curving back on itself like the surface of a sphere. Or it could be finite, open, and simply very much larger than the observable portion. Current measurements point toward a flat geometry. The Planck satellite, which mapped the cosmic microwave background in extraordinary detail, found the universe to be flat to within roughly half of 1%. What does flat mean in this context? It means that parallel lines stay parallel. It means light travels in straight lines that never converge or diverge. It means the geometry of space on the largest scales obeys Euclidean rules rather than the curved geometry you'd find on the surface of a sphere. A sphere has positive curvature. Parallel lines drawn on a sphere converge. If you start at the equator, draw 2 lines heading north, both perfectly parallel, they meet at the poles. A saddle shape has negative curvature. Parallel lines drawn on a saddle diverge. Our universe, to within our measurement precision, has 0 curvature, flat. And a flat universe can, in principle, be infinite. It doesn't have to be. A flat piece of paper is also flat, and pieces of paper have edges. But the mathematics allows an infinite flat universe, and there's nothing in the data that forces the universe to have a boundary. If the universe truly is infinite, that is not an abstraction. That is a literal statement about what exists. Every possible arrangement of matter that the laws of physics permit would, in an infinite universe, occur somewhere. Not metaphorically, not as a thought experiment. Physically, actually, somewhere in the vast beyond, including regions of space that look almost like ours. And, if you go far enough, regions that are, particle for particle, identical to ours. This is not philosophy. This is basic probability applied to infinite space. If there are infinite configurations of matter, and only finitely many distinct configurations are possible in any given region, then eventually, every configuration repeats. There would be regions of the universe beyond our horizon that are, right now, an exact duplicate of everything within 46 billion light-years of Earth, including this planet, including you. In this moment, not a copy, not a simulation. An actual physical instantiation of the same configuration of atoms. If the universe is truly infinite, that statement is not speculative. It's mathematical. Before we get to what might be out there, we need to understand something about why the horizon exists at all. Because the observable universe isn't a fixed thing. It's changing. Right now, light that left distant galaxies billions of years ago is still arriving at Earth. Every second, the boundary of what we can observe moves slightly outward. New photons arrive that have never been detected before. The observable universe is, in that sense, slowly growing. But here's the complication. The universe isn't just expanding. It's expanding at an accelerating rate. This was discovered in 1998, when two teams studying distant supernovae found something nobody expected. These were type Ia supernovae, a specific class of stellar explosion used as standard candles. A standard candle is an object whose intrinsic brightness you know. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. Type Ia supernovae are exceptionally useful standard candles because they arise from a very specific process. A white dwarf star in a binary system accretes material from a companion until it reaches a critical mass, about 1.4 times the mass of the Sun. At that mass, carbon fusion ignites throughout the star almost simultaneously. The star explodes. The explosion is always roughly the same brightness. Two teams, the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were independently measuring the brightness of distant type Ia supernovae to determine the expansion rate of the universe. They expected to find that expansion was slowing down. Gravity should be pulling things together. The expansion from the Big Bang should be decelerating. What they found was the opposite. The supernovae were fainter than expected. Not by a lot, just enough. Faintness means distance. The supernovae were further away than the expected deceleration should have placed them. The universe wasn't slowing down. It was speeding up. The expansion was accelerating. For this discovery, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. The only explanation that fit the data was that something was pushing the universe apart at an increasing rate. That something is called dark energy. It fills all of space. It has a constant energy density that doesn't dilute as the universe expands. As the universe grows larger, the total amount of dark energy grows with it, which means the acceleration increases. The more the universe expands, the more dark energy it contains, the faster it expands. Dark energy makes up about 68% of everything the universe contains. Dark matter makes up another 27%. All the normal matter, everything made of atoms, every star, planet, gas cloud, human being, spacecraft and telescope, adds up to roughly 5% of the universe's total energy content. 95% of what fills the cosmos is something we don't directly detect and don't fully understand. And the component we understand least, dark energy, is actively working to expand the universe faster and faster. This has a long-term consequence for the observable universe. Not today, not soon, but eventually, over timescales of hundreds of billions to trillions of years, the accelerating expansion means that distant galaxies will begin receding from us. Faster than light can cross the growing distance between us. Galaxy by galaxy, the observable universe will shrink. Galaxies that are currently visible will cross the cosmic horizon and disappear. Their light will be stretched to infinity, redshifted beyond detection, invisible. Astronomers in the very far future, if there are any, will look out at a universe that appears to contain only our local neighborhood. They'll have no evidence that billions of other galaxies exist. The cosmic microwave background will have been diluted to unmeasurable levels. The redshift data that showed us the universe was expanding will be gone. If they build cosmology from scratch, they'll conclude the universe is small and static and perhaps eternal. They'll be completely wrong, and they'll have no way to find out. This is unsettling for a reason that goes beyond the distant future. Because if this is what waits for astronomers in the far future, it raises an uncomfortable question about right now. What evidence of early cosmic structure has already expanded beyond our current horizon? What happened in the first fraction of a second after the Big Bang that we can no longer see? We have no way to know what we're missing. We can only study what the observable universe has preserved for us. And it may be that we live in an unusually information-rich epoch, sitting at the right moment in cosmic history to detect evidence of our origins before it recedes forever. In a few trillion years, that window will have closed. The record will be gone. The cosmic microwave background is the oldest thing we can see. It's the afterglow of the Big Bang itself, emitted roughly 380,000 years after the universe formed, when it had cooled enough for atoms to become stable and space to become transparent to radiation. Before that moment, the universe was a dense, opaque plasma. Photons couldn't travel freely. They were trapped, bouncing off charged particles in an endless fog. The universe was entirely opaque. No light could travel more than a tiny fraction of a millimeter before being absorbed and re-emitted. It was like trying to see through a wall of fire. Then, the fog cleared. The temperature dropped below roughly 3,000 Kelvin. At that temperature, protons and electrons could combine into stable hydrogen atoms without being immediately ripped apart by energetic photons. This transition is called recombination, and it happened across the universe within a relatively short window of time. When it did, photons were suddenly free to travel, and they've been traveling ever since. The cosmic microwave background is those photons, still crossing the universe, now stretched by billions of years of expansion into microwave wavelengths. The original light, emitted at 3000 Kelvin, would have been orange-red. Over 13 billion years of travel through expanding space, the wavelengths have been stretched by a factor of about 1,000. It now peaks in the microwave region of the spectrum, at a temperature of about 2.7 Kelvin, just barely above absolute zero. It arrives at Earth from every direction simultaneously. A perfect sphere of ancient light surrounding us at the furthest observable distance. When we map it, we're seeing a snapshot of the universe as it was over 13 billion years ago. The temperature is uniform to roughly 1 part in 100,000, almost perfectly smooth. But those tiny variations matter enormously. The slightly denser regions became the seeds of galaxies. The slightly less dense regions became the vast voids between galaxy filaments. Everything we see today, every spiral galaxy, every galaxy cluster, every cosmic void, grew from those ripples in the primordial plasma. The Planck satellite, which operated from 2009 to 2013, produced the most detailed map of the cosmic microwave background ever made. Its measurements refined our knowledge of the universe's age to 13.8 billion years, with an uncertainty of less than 1%. It measured the geometry of space to be flat within 0.5%. It determined the composition of the universe: 4.9% normal matter, 26.8% dark matter, 68.3% dark energy, all from studying temperature fluctuations of 30 millionths of a degree in ancient microwave light. Beyond the cosmic microwave background, there is no light we can receive. Not because there's nothing there, but because the universe before 380,000 years was opaque. This is our optical horizon, our deepest possible view using electromagnetic radiation, and it sits at roughly 46 billion light-years. But the universe at that time was already larger than what we can see. The region that emitted the light we now call the cosmic microwave background was itself a portion of an even larger, already expanding universe. So even our deepest view doesn't show us everything that existed at that moment. The universe beyond what emitted the cosmic microwave background we detect was already beyond our horizon, even at the very beginning. Inflation is the idea that fixes a problem. Actually, several problems. And it's the best framework we have for understanding what lies beyond the observable universe. In the 1970s and early 1980s, cosmologists noticed something strange about the cosmic microwave background. It was too uniform. Regions of the early universe that should have had no way to interact with each other, because they were separated by distances too large for light to cross in the time available, were at almost exactly the same temperature. If you look at two opposite sides of the sky, separated by 180 degrees, the cosmic microwave background temperature in those two directions agrees to 1 part in 100,000. But those regions were, in standard Big Bang cosmology, without inflation, completely causally disconnected at the time the cosmic microwave background was emitted. Light would not have had time to travel between them. They had never been in contact. They could not have reached thermal equilibrium with each other. And yet, they had almost identical temperatures. This was called the horizon problem. It had no clean explanation in standard Big Bang cosmology. There was a related problem called the flatness problem. The geometry of our universe is flat to within our measurement precision. But in standard Big Bang cosmology, flatness is an unstable condition. Like a ball balanced on top of a hill, If you start with a universe that's perfectly flat and then let it evolve, the tiniest deviation from flatness will grow over time. For the universe to be as flat as we observe it today, after 13.8 billion years of evolution, the initial conditions would have had to be tuned to flatness with extraordinary precision. Specifically, the initial density of the universe would have had to match the critical density to within about 1 part in 10 to the power of 60. 1 part in 10, followed by 60 zeros. That's an extraordinary degree of fine-tuning that standard Big Bang cosmology has no explanation for. And there was a third problem. Grand unified theories of particle physics, which attempt to unify the electromagnetic, weak, and strong nuclear forces, predicted that exotic particles called magnetic monopoles should have been produced in the early universe. Magnetic monopoles are particles with a single magnetic pole, either north or south, not the north-south pairs we find in every magnet. They should have been produced abundantly in the hot early universe. They should be everywhere. We've never found one. Inflation solves all 3 problems. In 1980, Alan Guth proposed that the universe, in its very earliest moments, underwent a period of exponential expansion. Not the relatively gentle expansion we see today. Something violent and extreme. A phase in which space itself doubled in size, then doubled again, then doubled again, and again, and again. So many times that in a tiny fraction of a second, the universe expanded by a factor of at least 10 to the power of 26. Possibly much more. This is inflation. Before inflation, the universe was small enough that all regions could interact. They had time to reach thermal equilibrium. They exchanged energy, reached the same temperature, and then inflation pulled them apart so rapidly that they appear disconnected today. But they weren't disconnected when they reached equilibrium. They reached equilibrium first. Then inflation happened. That's why the cosmic microwave background is so uniform. Inflation also solves the flatness problem. Whatever curvature the pre-inflation universe had was stretched out by the expansion. Any curve becomes approximately flat when you zoom in far enough. Inflation zoomed in by an enormous factor. The resulting geometry of space is flat to the precision of our measurements. Inflation solves the monopole problem by diluting any monopoles formed before inflation to the point where the chance of one occurring in our entire observable universe is negligibly small. And inflation explains where the tiny density fluctuations in the cosmic microwave background came from. This is perhaps the most remarkable part. The seeds of every galaxy, every structure we see in the universe today, came from quantum fluctuations. Tiny, random variations in energy density at the quantum scale, amplified by inflation to cosmic sizes. Before inflation stretched them, these fluctuations were smaller than an atomic nucleus. After inflation, they spanned the universe. And from those quantum seeds, over billions of years, the cosmic web grew. The filaments and voids and galaxy clusters that map the large-scale structure of everything. All of it traceable back to quantum randomness in the first tiny fraction of a second after the universe began. The evidence for inflation is strong. The spectrum of fluctuations matches inflation's predictions. The geometry is flat. The universe is homogeneous and isotropic on large scales. The monopole problem is resolved. And if inflation happened, then the universe that was inflated is vastly larger than what we can see. The observable universe is a small region of a much larger inflated space. The models disagree on how much larger, but many of them suggest the total universe is at least 10 to the power of 23 times larger than the observable portion. That number isn't a typo. 1 followed by 23 zeros. And that may be a conservative lower estimate for the most common inflation models. But inflation doesn't just produce a very large universe. In many of its formulations, it produces something else entirely. Something called eternal inflation. And this is where the physics becomes genuinely strange. Inflation is driven by a field, a physical entity that fills space and carries energy. Think of it like a ball sitting on a hill. While the ball is on the hill, it has potential energy. While the inflaton field is at high energy, inflation proceeds. When the ball rolls down and reaches the bottom, the potential energy converts to kinetic energy. When the inflaton field decays to a lower energy state, the energy converts into matter and radiation. This is called reheating. The hot, dense plasma of the early universe, the conventional Big Bang as we understand it, is what appears after reheating. In the simplest models, inflation begins, proceeds, and then ends uniformly. The whole universe reheats at once. The hot, dense plasma fills the universe, and the rest of cosmic history proceeds. But quantum mechanics complicates things. Because quantum fields don't evolve uniformly. They fluctuate. In some regions, the random quantum fluctuations kick the field back up rather than letting it decay, and those regions continue inflating. Here's the critical point. Inflation drives expansion so fast that a region where inflation continues grows faster than the rate at which inflation ends in nearby regions. The inflating space produces new volume faster than inflation ends. It never stops. It's called eternal inflation for exactly this reason. The framework was developed in the early 1980s by physicists, including André Linde, who proposed what he called chaotic inflation. In the chaotic inflation scenario, the inflaton field starts at different values in different parts of the primordial universe. Some regions roll down quickly and stop inflating. Others keep going. And the regions that keep going expand so fast that they come to dominate the volume of space. The inflating background is always the majority, by volume. Pockets where inflation ends are always the minority. In the framework of eternal inflation, our entire observable universe, everything within our 46 billion light-year horizon, is just one pocket in an endless ocean of inflating space. Here and there, throughout this infinite inflationary background, other pockets form. Other regions where the field decays. Other pockets where reheating occurs. Other histories begin. These pockets are causally disconnected from ours. The space between them inflates so rapidly that no signal can ever cross from one to another. They are separate regions with separate histories, each one a universe unto itself. And the number of these pocket universes, if eternal inflation is correct, is infinite. They are constantly forming, constantly separating from each other as the space between them inflates, constantly generating regions where the laws of physics are set by the value to which the field decays. Because quantum mechanics sets those values randomly, there is no reason to expect the laws in different pockets to match our own. Different constants of nature, different strengths of gravity, different masses for fundamental particles, a different periodic table, or no periodic table at all. Most of these pocket universes would be hostile to anything like life. Atoms might not form. Gravity might be too strong, collapsing everything into black holes before stars can ignite. Or too weak, leaving the universe so diffuse that matter never clumps. Or the proton would be unstable, decaying before chemistry could begin. The range of possible universes is, in many inflation models, enormous. And we happen to live in one that works. This brings us to one of the most debated ideas in modern physics: the anthropic principle. The observation that, whatever the range of universes that exist, we can only observe the ones compatible with our existence. Not because those are the only ones, but because observers can only find themselves in universes capable of producing observers. This sounds circular, and it is, in a certain sense. But it's also useful. It explains why we find ourselves in a universe with constants that permit atoms, stars, planets, and life, without requiring any special, external explanation for those constants. If there are enough universes with enough variation in their physical laws, some will have the right constants by chance. And only those will contain beings capable of asking why their universe has the right constants. We're here because we couldn't be anywhere else. This is either profound or deeply unsatisfying, depending on your temperament. Many physicists find it uncomfortable, because it seems to abandon the goal of explaining why the constants have the values they do. If the answer is just that we happen to be in a universe with compatible constants, and the others exist, but we can't see them, that feels like giving up. Like explaining why you won the lottery by noting that someone had to win it. Other physicists argue the criterion is being applied too strictly. We can't observe our own selection bias directly, but we can account for it. The universe we observe is necessarily one that permits us to observe it. That's not a tautology. It's a constraint. And constraints are what science works with. The debate is real, ongoing, and unresolved. What's clear is that the framework of eternal inflation and a multiverse is not arbitrary speculation. It follows from inflationary cosmology, which itself follows from the data. You don't have to invent it. It's what the mathematics produces when you take inflation seriously and combine it with quantum mechanics. There's another thing that might lie beyond the observable universe. And it's stranger than a multiverse of different physical laws. It comes from string theory. String theory is the leading candidate for a theory of everything. It attempts to unify quantum mechanics and general relativity, the two most successful theories in physics, which currently give contradictory predictions at extreme energies and densities. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Both theories are extraordinarily well tested. Both make predictions confirmed to extraordinary precision. General relativity predicted the bending of light around massive objects, confirmed by Eddington in 1919. It predicted gravitational waves, detected by LIGO in 2015. It predicted the existence of black holes, now directly imaged. Quantum mechanics predicted the fine structure of atomic spectra, the existence of antimatter, the behavior of semiconductors that make modern electronics possible. Every prediction tested, confirmed. And they disagree with each other at the Planck scale, the regime of extremely small distances and extremely high energies. At scales smaller than about 10 to the power of minus 35 meters, the two theories produce incompatible pictures. General relativity predicts a smooth spacetime that can curve and stretch. Quantum mechanics predicts that at small enough scales, spacetime itself fluctuates wildly. You can't use both simultaneously in those conditions. And situations where both matter, such as the interior of black holes and the moment of the Big Bang, are therefore beyond our current theoretical ability to describe. String theory attempts to resolve this by replacing point particles with tiny vibrating strings. The different modes of vibration correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. A graviton, the hypothetical particle mediating gravity, is a string vibrating in a specific mode. By treating gravity as just another vibration mode of the string theory automatically incorporates quantum gravity. The problem is that string theory requires extra dimensions. Not 3 spatial dimensions plus time, but 10 or 11 dimensions in total. The extra dimensions are curled up at a scale so small that we can't detect them, but they're there in the mathematics. And here's the complication. The way those extra dimensions are curled up determines the physical laws in the dimensions we can observe. The geometry of the extra dimensions sets the masses of particles, the strengths of forces, the value of the cosmological constant that drives dark energy. Everything we call the laws of physics emerges from the geometry of the hidden dimensions, and there are, according to some estimates, something like 10 to the power of 500 different ways the extra dimensions could be arranged. Each arrangement corresponds to a different set of physical constants, a different universe. 10 to the power of 500. That number is so large, it has no intuitive meaning. The number of atoms in the observable universe is roughly 10 to the power of 80. 10 to the power of 500 is incomprehensibly larger. You could make 10 to the power of 420 universes as large as ours, each filled to the brim with atoms, and still not have counted to 10 to the power of 500. And in this string theory landscape, as it's called, each possible compactification of the extra dimensions corresponds to a real physical possibility. Most string theorists believe that eternal inflation populates this landscape. As pocket universes form throughout the inflationary background, each one randomly selects one of those configurations. Each one is real. Each one persists. And across those configurations, almost any physical law that the mathematics permits is instantiated somewhere. The string landscape and eternal inflation together suggest that the multiverse isn't just large. It's exhaustive. Every configuration of physics that string theory allows is somewhere realized, in some pocket, in some region beyond our horizon, including the ones that produce nothing like structure, and including ours. It's worth stopping here and being honest about something. Everything described about eternal inflation and the string landscape is, in a strict scientific sense, not yet confirmed. Inflation is strongly supported, but not proven. The multiverse is a consequence of inflation, combined with quantum mechanics, but we haven't directly detected another universe. String theory remains the leading candidate for unification, but has not been empirically verified in any decisive way despite decades of effort. The string landscape is a mathematical result, not an observed fact. This is not a weakness of the ideas. It's an honest description of where physics stands. These are the best extrapolations from the best theories we have, applied rigorously to the data. They are what the mathematics produces. They may be wrong, but they are not uninformed guesses. They are the current frontier of theoretical physics, held at the edge between what we can test and what we cannot. The challenge is practical. If other pocket universes are separated from ours by inflating space, they are causally disconnected. No signal can cross the gap. No photon. No gravitational wave. Nothing. And if they're causally disconnected, they're in principle unobservable, which raises a question that philosophers and physicists argue about intensely. Is an unobservable universe a scientific concept at all? If we can never detect other universes, can we claim they exist in the same way we claim electrons exist? The debate has no clean resolution, but there's a possibility that offers a way out. In some models of inflation, pocket universes can collide. If two pockets form close enough together before the inflating space between them becomes too large, they can interact at their boundaries. The collision would leave a signature on the cosmic microwave background, a circular distortion in the temperature map, a region where the statistics of the background radiation differ from the expected random pattern. Cosmologists have looked for this. The Planck satellite examined the full sky map of the cosmic microwave background in detail. No confirmed pocket collision signature has been found. The current verdict is that there's no confirmed signature of a collision in our data. But the search continues. Future experiments will map the background with increasing precision. If a collision happened close enough and recently enough, its signature might be there, waiting for us to have the sensitivity to find it. It's also possible that collisions, while mathematically allowed, are so rare that we simply don't have one nearby. The absence of evidence for a collision is not evidence of absence of the multiverse. It's just information about our local neighborhood in the inflationary space. There's one more layer to this. One more possibility that sits at the outermost edge of speculative physics. And it comes not from inflation or string theory, but from quantum mechanics itself. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in 1957, says something radical about the nature of reality. In standard quantum mechanics, a particle exists in a superposition of states until it's measured. A quantum coin, before you look at it, is simultaneously heads and tails. When you measure it, the superposition collapses and you see one outcome. The other outcome disappears. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and others, says the collapse is real and complete. The other outcome doesn't exist. Measurement selects one branch of reality. Everett said something different. He said, the collapse is an illusion. What actually happens is that the universe branches. Both outcomes occur. In one branch, the coin is heads. In the other branch, the coin is tails. Both branches are equally real. The observer in each branch sees only their outcome because the branches don't interact after the split. If this is right, then every quantum event that could go multiple ways does go multiple ways in different branches. Every measurement, every interaction, every decay of every radioactive atom, everything that has a probabilistic outcome generates new branches. The universe is constantly splitting, constantly branching into a vast and growing structure of parallel realities. Everett's interpretation was largely ignored for decades after he proposed it. The physics establishment preferred Copenhagen, with its clear operational meaning: measure, get a result, repeat. But starting in the 1980s and accelerating through the 1990s, a growing number of physicists began taking Everett seriously. What changed wasn't new experimental evidence. What changed was a better understanding of decoherence. Decoherence is the process by which quantum superpositions appear to collapse when a quantum system interacts with its environment. A particle in superposition stays in superposition only while it remains isolated. The moment it interacts with even a single other particle, the superposition begins spreading into the environment. The quantum state becomes entangled with the environment's quantum state. And because the environment is enormously complex, the practical result looks identical to a collapse. The branches become inaccessible to each other. The different outcomes appear to separate into different classical realities. Everett's branches are decoherence in action. The universe isn't collapsing. It's entangling, spreading the quantum information into increasingly large systems until the branches are so different, so spread through so many particles, that no conceivable measurement could ever bring them back into interference. These branches don't exist beyond the observable universe in the sense that they're spatially further away. They exist alongside our universe in the mathematical space of all possible quantum states. This isn't geometry we can travel through. It's the abstract space that quantum mechanics uses to describe all possible configurations of a system. The branches coexist there, overlapping but non-interacting. Whether that means they're real in the same sense that the chair you're sitting on is real, is a philosophical question that physics alone can't answer. But the mathematics makes them unavoidable if you take quantum mechanics at face value, without adding any collapse mechanism. Many worlds is simply the Schrödinger equation taken seriously. And the branching it implies is, in numbers, almost unimaginably large. Every radioactive decay that has happened since the beginning of the universe has branched reality. Every quantum interaction in every star, every particle accelerator, every biochemical reaction in every living cell, every such event has forked the universe. There are more branches than there are particles in our observable universe. Far, far more. So what actually lies beyond the observable universe? The honest answer is that we have multiple serious candidates, and we can't yet definitively distinguish between them. More universe. Lots more universe. Extending beyond our horizon, with the same laws and the same kinds of galaxies and stars, and perhaps the same kinds of planets. An inflationary background, the eternally expanding space from which our observable universe emerged, and from which other pocket universes are still forming right now. Regions where the fundamental constants are different, where the same laws that produced us produce nothing, or produce something we couldn't recognize as matter. Quantum branches, a different kind of beyond, not spatial but logical, the other outcomes of every probabilistic event that ever occurred. These aren't competing in the sense that only one can be true. Some of them can be simultaneously correct. The universe beyond our horizon almost certainly extends further than we can see. If inflation is correct, the space beyond that is probably inflating. If quantum mechanics means whatever it said, the branches are a separate kind of beyond that exists regardless of cosmological models. The picture isn't one thing. It's layered. And the layers don't cancel each other out. Understanding what lies beyond the observable universe forces us to confront something uncomfortable about science itself. Falsifiability is usually considered a requirement for a scientific claim. A claim is scientific if it can, in principle, be tested. If there's some observation that could disprove it. The multiverse, in most of its forms, fails this test directly. We can't see other universes. We can't send probes there. We can't receive signals. And if we can't receive signals, there is no observation that could definitively disprove the claim that other universes exist. Some physicists argue this means the multiverse isn't science. It's speculation dressed in mathematics. A story we tell because the equations produce it, not because we can independently verify it. The philosopher Karl Popper argued that a theory is scientific only if it makes predictions that could, in principle, be falsified. By that criterion, the multiverse fails. It predicts everything, which is the same as predicting nothing. If every conceivable universe exists, there's no observation that could contradict the theory. Other physicists argue the criterion is being applied too strictly or to the wrong level. The multiverse isn't a direct claim about what we observe. It's a consequence of inflation and quantum mechanics, both of which are falsifiable. If inflation makes predictions about the power spectrum of the cosmic microwave background, and those predictions are violated, inflation is falsified. And if inflation is falsified, the inflationary multiverse collapses with it. The multiverse is testable through its parent theories, even if not directly testable itself. We can't directly observe quarks either. We infer them from the behavior of other particles. We can't directly observe the interior of a black hole. We infer conditions there from known physics and from signals that escape from the regions near the event horizon. The multiverse, in this view, is an inference from well-tested theories pushed to their logical conclusions. We observe inflation in its signatures. We observe quantum mechanics in its predictions. Both theories have been tested to extraordinary precision. If both theories are correct, the multiverse follows. Rejecting the multiverse while accepting inflation and quantum mechanics requires explaining why the logical consequences of those theories stop at a convenient boundary. And there's no clean answer to that. The status of the multiverse as science versus philosophy is genuinely unresolved. This is what progress at the frontier looks like. The questions are real. The tools for answering them are being built. The answers may take generations. To understand the beyond more deeply, we also need to understand something about the very early universe, the first fraction of a second, the regime where inflation supposedly happened and where the physics is most uncertain. We can probe this regime indirectly. The cosmic microwave background carries information about the physical state of the universe 380,000 years after the Big Bang. But the tiny temperature fluctuations we see in it are the imprint of what happened much earlier, during inflation. Those fluctuations were generated as quantum noise during inflation and then frozen into the geometry of space as inflation ended. The spectrum of those fluctuations, how the amount of variation changes with angular scale, is a direct record of inflation. Different inflation models make slightly different predictions for this spectrum. By measuring the spectrum with enough precision, we can narrow down which inflation models are compatible with reality. And inflation models differ in their implications for the beyond. High-energy inflation models tend to produce eternal inflation and a rich multiverse. Low-energy inflation models may produce a much simpler beyond. Just more of our universe, with the same laws extending further. The shape of the spectrum is therefore not just an academic parameter. It's a clue to the architecture of reality beyond what we can observe. There's another signal we're looking for, and it's potentially more informative. Primordial gravitational waves. During inflation, quantum fluctuations in the gravitational field would generate ripples in spacetime. Gravitational waves. These ripples would propagate through the universe and leave a distinctive imprint on the polarization pattern of the cosmic microwave background. Specifically, they would produce a pattern called B-mode polarization, a particular swirling arrangement in the way microwave photons are oriented. Scalar perturbations, the density fluctuations we already measure, cannot produce this pattern. Only tensor perturbations, gravitational waves, can. Finding B-mode polarization in the cosmic microwave background would be direct evidence for inflationary gravitational waves. It would tell us the energy scale at which inflation happened, and high-energy inflation is precisely the kind most likely to produce eternal inflation. The ratio between the amplitude of gravitational waves and density fluctuations is called R, the tensor to scalar ratio. Current measurements constrain R to be less than about 0.1. That's an upper limit. We haven't detected the signal yet. But we've narrowed down where it could be. The BICEP experiment at the South Pole detected what appeared to be a B-mode signal in 2014. It was announced with considerable excitement. But subsequent analysis showed that the signal was contaminated by thermal emission from galactic dust. The cosmic signal, if present, was buried under galactic foregrounds. The claimed detection didn't hold. But the tools improved. The Simons Observatory, currently under construction in the Atacama Desert in Chile, will have roughly 10 times the sensitivity of previous experiments. CMB-S4, a next-generation experiment planned for the late 2020s, will push sensitivity further still. If there's a primordial B-mode signal at a level physics predicts from high-energy inflation, these experiments will find it. If they don't find it, that constrains inflation to lower energies, with different implications for the beyond. Either result is informative. Either result moves us forward. There's something to appreciate about the precision physicists have achieved in studying the early universe. The temperature fluctuations in the cosmic microwave background are 30 millionths of a degree. To detect such tiny variations across the full sky, experiments need to be extraordinarily sensitive. The Planck satellite was cooled to temperatures colder than the space around it. Its detectors were cooled to within 1/10 of a degree of absolute zero. At that temperature, the thermal noise in the detectors was reduced to a level where genuine cosmic signals could be measured. The result was a map of the universe when it was 380,000 years old, with temperature resolution better than 30 millionths of a degree, across the entire sky. From that map, cosmologists extracted the power spectrum, how much temperature variation there is at each angular scale. The spectrum shows a characteristic series of peaks. These peaks are called acoustic peaks. They come from sound waves in the early universe plasma. Before recombination, the universe was a plasma. Photons and baryons, the protons and electrons that would later form atoms, were tightly coupled. They behaved as a fluid. And in that fluid, density variations set up oscillations, sound waves, compressing and expanding, like sound waves in air. But in the early universe, plasma, the amplitude of those sound waves at the moment of recombination is frozen into the cosmic microwave background pattern. The first acoustic peak in the power spectrum corresponds to a scale that had just enough time to compress once before recombination. The second peak corresponds to a scale that compressed and then rarefied. The third peak compressed, rarefied, and compressed again. The positions and heights of these peaks encode an extraordinary amount of information. The baryon density of the universe, the total matter density, the geometry of space, the expansion rate, all extractable from the same map of ancient temperature fluctuations. This is one of the great achievements of observational cosmology. The ability to read the detailed properties of the early universe from ancient light. And it's the same framework we'll use to probe the physics of inflation, which is the physics of the beyond. There's something worth understanding about what the universe looked like before the cosmic microwave background formed, before 380,000 years. The first 3 minutes of the universe are actually well understood. Not perfectly, but surprisingly well. The physics of the first 3 minutes involves nuclear reactions, the same nuclear physics we study in laboratories and power plants. Protons and neutrons combining to form atomic nuclei. The process called Big Bang nucleosynthesis. In the first 3 minutes, the universe was hot and dense enough for nuclear fusion. Protons and neutrons slammed together and stuck. Deuterium formed, then helium-3, then helium-4, then tiny amounts of lithium. By the time the universe was about 3 minutes old, it had cooled enough that nuclear fusion stopped. The nuclei that had formed were frozen in. The final product was about 75% hydrogen and 25% helium by mass, with trace amounts of other light elements. And that's what we observe today. The oldest, most pristine regions of the universe, where stars haven't had time to process the original material significantly, show almost exactly that composition. The agreement between the prediction from Big Bang nucleosynthesis and the observed elemental abundances is one of the strongest confirmations of the Big Bang model. But it also tells us something about the beyond. If the universe beyond our horizon formed in the same way, if inflation produced a large region with the same fundamental physics that then underwent reheating and nucleosynthesis, then the elemental composition beyond our horizon should be similar to ours. Hydrogen and helium, the raw material for stars, unless the constants are different there, in which case nucleosynthesis would proceed differently. Different proton to neutron ratios, different binding energies for nuclei, different fractions of hydrogen and helium, or perhaps no stable nuclei at all if the fundamental interactions have different strengths. The elemental composition of a region of the beyond is therefore a direct consequence of its physical constants. And the physical constants are, in eternal inflation, set by the random quantum decay of the inflaton field. The beyond is, in this sense, a random draw from a distribution of possible physical laws. And we happen to be in the draw where the laws work. There is a version of the beyond that doesn't require a multiverse or inflation. It just requires the universe to be very large and for the geometry to be flat. If the universe extends far beyond our observable horizon with the same average density and the same physical laws, then the observable universe is a small sample of that larger whole. And in a sufficiently large universe with finite possible configurations per region, repetition is inevitable. The physicist Max Tegmark worked out the numbers. Given the quantum states possible in a region the size of our observable universe, and given that configurations must eventually repeat in a sufficiently large space, he estimated the approximate scale at which near-identical copies of our observable region must appear. The number is roughly 10 to the power of 10 to the power of 118 meters away. A 1 followed by 10 to the power of 118 zeros. The number of digits in that number exceeds the number of particles in the observable universe by an incomprehensible margin. But the point isn't the specific number. The point is that in an infinite universe, or even a sufficiently large finite one, the repetition is mathematically inevitable. There would be, somewhere in the vast beyond, a region of space almost identical to our observable universe, with a galaxy almost identical to the Milky Way, with a star almost identical to our Sun, with a planet almost identical to Earth, and everything on it. Not a copy, not a parallel dimension, a physical reality, made of the same atoms obeying the same laws, having followed almost the same history. The only difference from a perfect copy would be tiny quantum fluctuations that accumulated over billions of years and led to slightly different outcomes. But it would be close. In an infinite universe, there would be infinitely many such regions. This is not an exotic claim. It follows from the most basic assumptions: that the universe is large enough, that the laws of physics are the same everywhere, and that matter is distributed roughly uniformly on the largest scales. All of those assumptions are consistent with everything we observe. There's something that almost never gets mentioned in discussions of the observable universe and its limits. The light we see from distant galaxies isn't just old. It's evidence of a relationship we can no longer maintain. When a galaxy is close enough, the space between us and it is expanding slowly enough that light can cross it. We could, in principle, send a signal. A photon headed in the right direction would eventually reach that galaxy, even accounting for expansion. But galaxies beyond a certain distance are receding so fast that even a light signal sent now could never catch them. The space between us and them is expanding faster than light can cross it. Not because the galaxy is moving faster than light through space. Space is not a material that moves, but the amount of new space appearing between us and them every second is more than 300,000 kilometers. More than light can traverse in a second. These galaxies are beyond what's called our cosmic event horizon. It's different from the edge of the observable universe. We can still see galaxies beyond our cosmic event horizon. Their past light is still arriving. We are still receiving photons emitted by those galaxies millions and billions of years ago. But nothing we send now can ever reach them. And the galaxies on the other side of that horizon can never receive any signal we emit from this moment onward. We are already, right now, causally isolated from a vast portion of the universe. The light we receive from those galaxies is a historical record, evidence of a relationship that no longer has a future. We see them as they were. We cannot influence them as they are, and they cannot know we're here. Over time, as the expansion continues to accelerate, more and more galaxies will cross that horizon. The universe is not just expanding, it's partitioning, isolating regions from each other at an accelerating rate. The future is one of increasing cosmic isolation, not in any timescale that matters for life as we know it, but in the timescales physics permits. The universe is actively severing connections between regions that were once able to communicate. There's a signal from the very early universe that physicists hope to eventually detect. The gravitational wave background from the first fraction of a second. Gravitational waves pass through matter as if it weren't there. Unlike light, which was scattered continuously in the early plasma until recombination, gravitational waves from the inflation epoch travel through everything. They have been propagating through the universe, essentially undisturbed since the moment they were created. If we could detect them, we would be receiving a signal from the very beginning, not from 380,000 years. From the moment inflation ended. The physics at that moment is the physics of the beyond, the energy scale of inflation, the nature of the inflaton field. Whether inflation was driven by a single field or multiple fields, whether it ended gradually or abruptly. All of this is encoded in the spectrum of primordial gravitational waves. The challenge is sensitivity. These waves are ancient and have been diluted by billions of years of expansion. Their amplitude today is extraordinarily small. Ground-based detectors like LIGO, sensitive enough to detect gravitational waves from merging black holes billions of light-years away, are still orders of magnitude too insensitive for the primordial background. LISA, the Laser Interferometer Space Antenna, is planned for launch in the mid-2030s. It will detect gravitational waves at frequencies impossible for ground-based detectors, including, potentially, background signals from high-energy processes in the early universe. A space-based interferometer, with arm lengths of millions of kilometers, would be sensitive in frequency ranges that ground-based detectors can't access. Each of these instruments is another tool for probing the physics that created what lies beyond our horizon. Not seeing beyond it directly, but understanding the process that made it. By learning that physics with increasing precision, by constraining the inflation models, by refining our understanding of dark energy and quantum gravity, we are indirectly learning about the beyond. Mapping it not with light, but with reasoning built on data. And there's something important to say about that process. Indirect evidence isn't second-rate evidence. It's often the only kind available. We've never directly observed the inside of a proton, but we've inferred its internal structure from scattering experiments with extraordinary precision. We've never directly observed a single neutrino born in the Big Bang. But we've inferred the relic neutrino background from multiple independent lines of evidence. We've never directly observed a quantum of dark matter, despite it making up 27% of the universe. But we've inferred its existence from gravitational effects on galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, and the structure of the cosmic microwave background. All indirect, all solid. The beyond is, in a sense, no different. We haven't seen it. We can reason about it. And if the reasoning is built on well-tested physics, the conclusions are trustworthy, even without direct confirmation. This is the method. This is how science extends itself past the direct reach of instruments. It isn't guessing. It isn't faith. It's the disciplined application of what we know to domains where we can't yet look. And sometimes, the indirect conclusions turn out to be right in ways that surprise us. Maxwell calculated that electromagnetic waves should propagate at the speed of light, and concluded that light was an electromagnetic wave, before anyone had generated a radio wave in a laboratory. Dirac predicted the positron from the mathematics of quantum electrodynamics, before any experimenter had found one in a particle detector. Chandrasekhar calculated that stars above a certain mass must collapse when they burn out, before the observational evidence for neutron stars and black holes was in. In each case, the mathematics outran the data, and the mathematics was right. The beyond is our current version of that. The mathematics of inflation and quantum mechanics outrun our instruments. But there's no particular reason to think they're wrong. The question of what lies beyond the observable universe matters for reasons that aren't purely academic. It speaks directly to the deepest question we can ask. Why is there something rather than nothing? Why are the laws of physics what they are? Why is the universe structured in a way that permits complex chemistry, which permits biology, which permits the kind of consciousness that can ask these questions? For most of human history, these questions had no scientific answer. They were left to philosophy and religion. But modern physics has produced a framework that actually engages with them scientifically. If there are infinitely many universes with infinitely many configurations of physical law, then the question of why the constants have the values they do has an answer. They don't all have the same values. Ours have the values they do because we're in a universe where they produce observers. This isn't a satisfying answer in the way a simple mathematical derivation would be satisfying. But it's a real answer. An answer consistent with everything we observe. And it connects directly to what lies beyond the observable universe. Beyond our horizon, if eternal inflation is correct, are regions with different answers to those questions. Different constants. Different outcomes. Regions where the question of why things are as they are has no observer to ask it. Because nothing complex enough to ask questions ever formed. We are, in this picture, an outcome. Not the intended outcome. Not the only outcome. Just one of the outcomes, in a space of possibilities large enough that eventually a universe like ours appears. And that reframing, from unique to inevitable, from special to statistical, is perhaps the most Copernican shift physics has made in the last century. Copernicus removed Earth from the center of the solar system. Hubble showed that the Milky Way is not the center of the universe. Modern cosmology now suggests that our observable universe might not even be the center of the multiverse. That our physical constants, the values we consider fundamental and precise, might simply be the values in this particular draw from a cosmic probability distribution. Each step has moved us further from the center. Each step has been uncomfortable. Each step has ultimately been correct, as far as we can tell. The Copernican principle, the idea that we don't occupy a special position, seems to apply not just to space, but to the space of possible universes. We're not at the center of the multiverse. We're not in the most common type of universe. We're in one of the subset that permits observers. And that subset, vast as it might be in absolute numbers, is likely a tiny fraction of all possible configurations. The universe is not fine-tuned for us in the sense that someone adjusted the controls. It's fine-tuned for us in the sense that we couldn't exist to observe it if it weren't, which is a very different kind of fine-tuning, one that requires no fine-tuner, just a large enough space of possibilities. There's something to appreciate about where we sit in the history of this question. For most of human history, the universe was small, not metaphorically, literally. The Earth was the center. The stars were lights on a sphere overhead. The sphere wasn't very far away. In the 16th century, When Copernicus placed the sun at the center, the universe expanded. When Galileo pointed a telescope at the sky and saw moons orbiting Jupiter, the scale expanded again. In the 1920s, when Edwin Hubble measured the distance to what had been called nebulae and found they were separate galaxies millions of light-years away, the universe expanded by a factor the mind could barely absorb. When Hubble measured the redshift of those galaxies and found the universe was expanding, the universe grew again, backwards through time to a beginning. In 1980, when Guth proposed inflation, the universe grew by at least 10 to the power of 26 in a fraction of a second. And if inflation is eternal, the growth is infinite. Every time we've pushed the question, the answer has been bigger than we thought. Not a little bigger. Absurdly, incomprehensibly, embarrassingly bigger. There's a pattern there. And the pattern suggests that whatever we think lies beyond the observable universe, the truth is probably larger, more complex, more surprising. Not because we're pessimistic about our own understanding, but because that's what the history of this question consistently teaches. The universe doesn't fit inside our intuitions. It never has. Every time we've tried to place a boundary on it, the boundary has moved. The cosmic microwave background is our window to the earliest light. But there's something even older than light that passed through the opaque early universe, essentially undisturbed. Neutrinos. These are elementary particles with almost no mass and no electric charge. They interact with matter so weakly that they could pass through a light year of solid lead with barely a chance of interacting. In the early universe, when the temperature was high enough, neutrinos were in thermal equilibrium with everything else. They were constantly being created and absorbed. But roughly 1 second after the Big Bang, the universe had expanded and cooled enough that neutrinos decoupled. They stopped interacting with other matter. They streamed freely through space, and they've been doing so ever since. There is, in principle, a cosmic neutrino background, analogous to the cosmic microwave background. A bath of ancient neutrinos pervading all of space, carrying information about the universe when it was 1 second old, 303,000 years before the cosmic microwave background was emitted. We cannot currently detect it. The relic neutrinos have energies so low that our detectors can't reliably separate them from background noise. But they're there. Right now, about 336 relic neutrinos pass through every cubic centimeter of space, in every direction, every second. You're immersed in ancient particles from the first second of the universe's existence. They pass through you without a trace. And beyond the observable universe, in whatever lies out there, the same neutrino background almost certainly exists. A universal constant, shared across any region of the cosmos with similar physics. Even if we can't see what's beyond our horizon, we know something about it. The same background radiation that pervades our space almost certainly pervades it, unless the laws are truly different there. In which case, everything about the beyond might be unrecognizably alien. It's worth spending a moment on what we actually expect the beyond to look like in physical terms. Not the exotic multiverse, not the quantum branches. Just the ordinary, plain extension of the universe beyond our current horizon. What's there? Our best answer, based on everything we know about cosmology, is more of the same. More galaxies. More galaxy clusters. More filaments of the cosmic web stretching between them. More vast voids. more of the large-scale structure we map in the observable universe. The cosmic web, the network of filaments and sheets of galaxies surrounding enormous empty voids, is the dominant structure of the observable universe. When you look at maps of galaxy positions covering billions of light-years, what you see is unmistakable. Galaxies cluster along thin filaments. The filaments connect at nodes, where the densest galaxy clusters sit. Between the filaments, vast voids, nearly empty of galaxies, stretching hundreds of millions of light-years across. The whole structure looks, in two dimensions, like a cosmic foam, or like a three-dimensional spider's web, or like the structure of neurons in a brain. The resemblance to biological structures is coincidental. The physics is purely gravitational. Dark matter concentrated in filaments, attracting normal matter. Normal matter forming galaxies along those filaments. Gravity pulling galaxies along filaments toward the nodes. Gravity running away from the voids, evacuating them. The result is this remarkable web. The Laniakea supercluster, the structure that contains our local group of galaxies, spans roughly 500 million light-years. It contains the mass of 100 quadrillion suns, about 100,000 galaxies. And Laniakea is just one node in the larger cosmic web. The Perseus-Pisces supercluster stretches roughly 250 million light-years. The Coma supercluster is another enormous structure containing thousands of galaxies. The Sloan Great Wall, discovered in 2003, spans roughly 1.37 billion light-years. One of the largest confirmed structures in the observable universe. But all of these sit within a larger web that extends in all directions to the edge of what we can see. And beyond our horizon, the same web continues. The same dark matter filaments, laid down by the same quantum fluctuations during inflation, on the same scales, following the same statistics. The specific galaxy positions are different. The random quantum draw was different beyond our horizon. But the large-scale pattern, the filaments and voids and nodes, is statistically the same. The universe beyond our horizon looks, on large scales, very much like ours. How do we know this? Because the cosmic microwave background shows us the statistical properties of the fluctuations that seeded the large-scale structure. Those fluctuations are the same throughout the inflated region, following a specific statistical pattern called a nearly scale-invariant power spectrum. A power spectrum that Planck has measured with high precision. That same power spectrum, that same statistical fingerprint, is what inflation laid down everywhere in the inflated space. The cosmic web we see is one realization of that statistical fingerprint. The beyond contains other realizations of the same fingerprint, different in detail, the same in statistics. Like different pieces of fabric woven on the same loom, from the same pattern, but with natural variation in the thread. The cosmic web extends far beyond what we can see, probably for an enormous distance, until you hit the region where the physics changes, if it changes. If eternal inflation is correct, you'd eventually hit the boundary between our pocket and the inflating background. But that boundary, if it exists, is almost certainly far beyond the region where structure is the same as ours. The ordinary beyond is vast, filled with galaxies, filled with stars, filled with whatever forms around those stars. The exotic multiverse lies beyond the ordinary beyond. But the ordinary beyond is already overwhelming in scale. There's something to appreciate about the sheer scale of what we don't know, and how different it is from not knowing small things. Not knowing whether a distant planet has liquid water is a specific, bounded question. The answer is somewhere in the data, waiting for better instruments. Not knowing what lies beyond the observable universe is a different kind of not knowing. It's not a question of insufficient data. It's a question of fundamental limits. The speed of light is constant. The age of the universe is finite. Those two facts together impose a hard boundary on what any intelligence, anywhere in our observable universe, can ever see by looking out with telescopes. No matter how advanced the technology, no matter how sensitive the instruments, the limit is the limit. This is humbling in a way that's different from ordinary scientific uncertainty. Most of the things we don't know yet. More experiments, more data, more clever analysis will answer them. But this particular question, what lies beyond the observable universe, will likely never be answered by direct observation. It will be answered, if at all, by inference. By building theories so powerful and so well confirmed in what we can test that their implications for what we can't test become trustworthy. By finding indirect signatures, like bubble collision marks in the cosmic microwave background, or the detailed statistics of inflation's fingerprint in the temperature power spectrum, by pushing theory until the predictions become unavoidable. That is a different kind of science than measuring and confirming. It's reasoning under permanent uncertainty, and it's genuinely hard. But it's not the same as giving up. It's not the same as speculation. It's the oldest scientific tradition applied to the hardest question, figuring out what must be true given what we know. As you sit with this tonight, it's worth letting the scales settle without trying to grasp it all at once. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions to trillions of stars. Each star is a nuclear furnace, burning for billions of years. And all of that, every single particle of it, every photon ever emitted, every black hole ever formed, every planet ever assembled, every atom ever forged in a stellar core and scattered by an explosion, is a small region of what probably exists. A tiny patch in an enormous or infinite cosmos. And we are here, on one of those particles, looking out, with instruments built from the atoms around us, with mathematics developed by minds that evolved to track prey across a savanna and interpret the expressions on other people's faces. And somehow, with those instruments and that mathematics, we have sketched the rough outline of what lies beyond what we can see. We haven't reached it. We probably never will. But we have described it. We have reasoned about it, honestly, using our best understanding of how reality works. And the description, with all its uncertainties, is extraordinary. More universe, more physics, more possibilities than any single universe, including ours, could exhaust. The observable universe is not the world. It's our neighborhood, and the neighborhood has no visible edge. That's not a poetic statement. That's the current, best supported picture of reality. And every time we've thought the universe was smaller than it actually is, we've been wrong. There's no particular reason to think this time is different. There's a version of the beyond, proposed by the mathematician and physicist Max Tegmark, that's worth sitting with for a moment. Not because it's the most likely, but because of what it forces you to consider. Tegmark has argued that the universe isn't just described by mathematics. The universe is a mathematical structure. not a physical thing that happens to be describable by equations. An actual mathematical object. And if this is correct, then every self-consistent mathematical structure exists as a physical reality. Not every conceivable universe. Only those described by self-consistent mathematics. But the set of self-consistent mathematical structures is, to put it mildly, large. Every set of physical laws that doesn't internally contradict itself corresponds to a real universe somewhere. This is the most extreme version of the multiverse idea. It encompasses not just the range of universes accessible via eternal inflation and string theory. It includes universes with completely different mathematical foundations. Universes where space-time has a different number of dimensions. Universes where the rules of logic itself are different. Universes describable by equations we haven't invented yet. The mathematical universe hypothesis is not widely accepted. It's speculative in a way that goes beyond even eternal inflation and string theory. But it illustrates the logical endpoint of the reasoning. If you follow the logic of different physical constants, different physical laws, different dimensions of space, you eventually reach a position where any consistent set of rules for a universe is real. And that position is almost impossible to distinguish from the claim that everything imaginable and everything unimaginable exists, which is either the deepest possible insight about reality or a sign that the reasoning has outrun the data. Physicists disagree on which. That's not unusual for the frontier. The question of the universe's topology is separate from its geometry, and it's worth understanding. Geometry describes how space is locally curved. Topology describes the overall shape and connectivity of space. A flat universe, geometrically, could have a topology that makes it finite. Imagine cutting a flat piece of paper into a square, then gluing opposite edges together. What you get is a torus, the surface of a donut. The local geometry is flat, but the overall topology is closed. If you travel in one direction on a torus long enough, you return to where you started. The same is possible for the universe. A universe with flat geometry could be topologically closed, looping back on itself. If it does, then there's no beyond in the usual sense. Traveling far enough in any direction brings you back to the same region. The universe folds back on itself. In this scenario, the observable universe would be a portion of a larger structure that eventually wraps around. If the universe is small enough, we might even see the same galaxy twice, once in its current position and once as light that went the long way around the universe and arrived from the opposite direction. We've looked for this. Cosmologists have searched for pairs of galaxy clusters that appear in different parts of the sky, but are actually the same cluster seen from different directions. They've looked for matched patterns in the cosmic microwave background, the same temperature pattern appearing in multiple spots. None have been found, which doesn't rule out a closed topology. It just constrains it. If the universe wraps back on itself, it's at least as large as the observable universe. Probably much larger. So, even a topologically closed universe has a lot of beyond. It just eventually connects back. Dark energy is the most abundant thing in the universe, and we have almost no idea what it is. We know what it does. It drives the accelerating expansion. We know its effect on the geometry and structure of the universe, but its nature is profoundly uncertain. The simplest explanation is that dark energy is a cosmological constant. a fixed energy density that fills all of space. Einstein introduced the cosmological constant in 1917, before the universe was known to be expanding, as a way to make the universe static. He called it his greatest blunder when the expansion was discovered. But nature apparently uses it anyway. In quantum field theory, the vacuum isn't empty. It's filled with quantum fluctuations. Virtual particles constantly popping in and out of existence. This vacuum energy has a non-zero energy density. And a non-zero energy density in the vacuum, if it doesn't dilute as space expands, would behave exactly like a cosmological constant. It would drive acceleration. The problem is that when physicists calculate the expected vacuum energy from quantum field theory, they get a number. And when they measure the actual energy density from cosmological observations, they get a number. Those two numbers disagree by about 120 orders of magnitude. 10 to the power of 120. This is not a rounding error. This is the largest discrepancy between theory and observation in all of physics. Either our theory of vacuum energy is catastrophically wrong, or something is cancelling almost all of the vacuum energy with extraordinary precision, leaving only a tiny residual. The mechanism for that cancellation is unknown. This is the cosmological constant problem, and it's one of the deepest unsolved problems in theoretical physics. Some physicists argue that the anthropic principle solves it. In a multiverse, where the cosmological constant takes different values in different pocket universes, most values would either cause the universe to expand so fast that matter never clumps, or cause it to recollapse before structure can form. Only a narrow range of values permits galaxies, stars, and planets. We observe a value in that range because we couldn't exist in a universe with any other value. This is plausible. It also means the cosmological constant tells us something about the multiverse, if the multiverse exists. The observed value is exactly the range that would be selected for in a landscape of universes where the cosmological constant varies, which is a circumstantial but real argument in favor of the multiverse. Alternatively, dark energy might not be a cosmological constant at all. It might be a dynamic field, something like the Inflationary field, that changes over time. If dark energy is changing, the acceleration of the universe's expansion might be different in the past than it is now, and it might change in the future. Some models of dynamic dark energy predict that the acceleration will eventually stop and reverse. The universe would slow its expansion, stop, and begin contracting, eventually collapsing back into a hot, dense state. Not quite a reverse Big Bang, but something like it. A big crunch. Other models predict the opposite. Dark energy, growing stronger over time, eventually overwhelming all the other forces. First, tearing apart galaxy clusters. Then, individual galaxies. Then, solar systems. Then, planets. Then, atoms. A big rip, in which space itself tears apart all structure down to the subatomic scale. Current observations don't definitively distinguish between a cosmological constant, where the acceleration is permanent, and dynamic dark energy, where it might change. The data is consistent with a constant. But within the error bars, there's room for slow variation. This is an active area of research. The Euclid mission, launched in 2023, is mapping hundreds of millions of galaxies to measure the expansion history of the universe with unprecedented precision. By measuring exactly how the expansion rate has changed over the past several billion years, Euclid will constrain dark energy models far more tightly than before. And the answer will matter for the beyond. If dark energy is constant, the future is permanent acceleration. Increasing isolation. Everything outside our local group, eventually beyond reach. If dark energy is dynamic, the future is less certain. And that uncertainty is itself information about the nature of what drives the expansion. There's an idea in theoretical physics called the holographic principle, and it changes how physicists think about what the beyond even is. The holographic principle emerged from black hole thermodynamics in the 1970s and 1980s. The physicist Jacob Bekenstein showed that a black hole has entropy proportional to the area of its event horizon, not to its volume. Entropy is a measure of information, of the number of possible configurations of a system. In ordinary physics, entropy scales with volume. A bigger box can hold more information than a smaller box. But for a black hole, the information it contains is proportional to the surface area, not the volume enclosed. This was strange. Stephen Hawking built on Bekenstein's work to show that black holes are not just information storage. They radiate. Hawking radiation carries information away from the black hole, slowly, over very long timescales. And the temperature of that radiation is inversely proportional to the mass of the black hole. Smaller black holes are hotter. Larger black holes are colder. These ideas led to a profound question. If a black hole's information content is encoded on its surface rather than in its volume, maybe that's true of all of space. Maybe the information content of any region of space is encoded on its boundary. Maybe the universe itself is, in some deep sense, a hologram. Not a hologram in the everyday sense, but in the sense that all the information needed to describe the three-dimensional interior of a region is encoded on the two-dimensional surface surrounding it. The holographic principle was formalized by Gerard Hooft and Leonard Susskind in the 1990s, and it received its clearest mathematical realization in 1997, when Juan Maldacena proposed what is now called the anti-de Sitter, conformal field theory, correspondence, or ADS, CFT. Maldacena showed that a specific theory of quantum gravity in a particular type of curved spacetime is mathematically equivalent to a specific quantum field theory, without gravity, on the boundary of that spacetime. The two theories describe the same physics. But one is a three-dimensional gravity theory, and the other is a two-dimensional non-gravity theory. They're dual descriptions of the same reality. This was revolutionary. It demonstrated that gravity in a bulk space can be exactly equivalent to a lower-dimensional theory without gravity on the boundary. The interior of a space-time region is in some sense redundant, because all the information is already encoded on the boundary, and it has implications for how we think about the beyond. If the holographic principle is correct, then what lies beyond the observable universe isn't just more space with more galaxies. It's connected to what's inside our horizon through the information encoded on boundary surfaces. The physics of horizons, of surfaces, of boundaries is more fundamental than the physics of bulk space. And the edge of the observable universe is one of the most fundamental surfaces there is. There's a class of models in cosmology that propose a universe before the Big Bang, not instead of the Big Bang, but before it. In standard cosmology, the Big Bang is the beginning. Time began. The question of what came before is not just unanswered. It's considered meaningless because there is no before. But several theoretical frameworks question this. The Cyclic universe model, developed by Paul Steinhardt and Neil Turok in the early 2000s, proposes that the Big Bang was not the beginning. It was a transition. In their model, our universe is one membrane, a brain, in a higher dimensional space. A parallel brain exists nearby. Every trillion years or so, the two brains collide. The collision produces enormous energy. It looks like a Big Bang. Our current universe is the aftermath of the most recent such collision. Before this collision, there was a previous universe. Before that, another one. The cycle may be eternal. No beginning, no end. Just an infinite series of collisions, expansions, cooling, and contractions. If this model is correct, the beyond isn't just spatially vast. It's also temporally vast, infinitely deep in time, containing an infinite succession of universes, each one a cycle of the same basic structure. The cyclic universe model makes specific predictions about the cosmic microwave background. It predicts no primordial gravitational waves, or very weak ones. This contrasts with high-energy inflation models, which predict a detectable gravitational wave signal. If CMBS4 searches for primordial B-mode polarization and finds nothing, that would be consistent with the cyclic model, and inconsistent with high-energy inflation, which doesn't prove the cyclic model. But it narrows the field. Loop quantum cosmology provides another perspective on the pre-Big Bang. Loop quantum gravity proposes that space itself is not continuous. At the Planck scale, roughly 10 to the power of minus 35 meters, space is discrete, granular. In this framework, the Big Bang singularity doesn't exist. The singularity, the mathematical point of infinite density, is an artifact of applying general relativity beyond its domain of validity. When quantum gravity effects are included through loop quantum cosmology, the singularity is replaced by a quantum bounce. The universe contracts to an extremely high density, but not to a mathematical singularity. Then it bounces, expands outward. What we call the Big Bang is the outgoing phase of a bounce from a previous contracting phase, a previous universe. In the loop quantum cosmology picture, there may have been a universe before ours. It contracted, hit the quantum bounce, and expanded into what we experience. These models represent genuine alternatives to eternal inflation as explanations for what generated the initial conditions we observe. They don't require the inflaton field, but they do require a beyond of a different kind. Not a spatial beyond, a temporal beyond, a universe before ours, or an infinite series of universes cycling through time. There's a question that sits beneath all of this, and it's worth naming directly. If the beyond is infinite, if there are infinitely many pocket universes, if there are infinitely many branches from quantum mechanics, if there are infinitely many cycles of a cyclic universe, then in what sense does any of it matter? If everything that can happen does happen, infinitely many times, in infinitely many versions, then are our choices, our history, our individual existence meaningful in any way? This is a genuine question, not a rhetorical one. The traditional answer to why things matter has often been that they're unique. This moment, this universe, this life is the only one. What happens here is unrepeatable. If the multiverse is real, That argument doesn't hold in the same way. Every moment is repeated. Every choice plays out in every possible direction. Every life is played out in every possible variation, somewhere. Some people find this liberating. Others find this deeply uncomfortable. If nothing is unique, if everything is repeated infinitely, then meaning seems to dissolve. There's no clean answer to this. It's a philosophical question, not a physics question. But it's the question that the physics raises, and it's worth taking seriously. What the physics tells us is that the universe beyond our horizon is vast, possibly infinite, and possibly filled with variations on everything we know. What that means for how we ought to live is not something physics can answer. But the question only arises when you take the physics seriously. And taking the physics seriously is, in itself, a form of engagement with what's real. There's a connection between the physics of the beyond and the physics of the very small that's worth exploring. Because the biggest structures in the universe and the smallest particles we know are connected in ways that aren't obvious. The structure of the universe on the largest scales, the cosmic web of filaments and voids, came from quantum fluctuations. The tiny random variations in energy density during inflation, smaller than a proton, were stretched to cosmic scale. Those variations became the seeds of everything. The positions of galaxies, the shapes of galaxy clusters, the locations of voids, all of it traces back to quantum randomness in the first tiny fraction of a second. Quantum mechanics determines where galaxies are. And here's the implication for the beyond. The universe beyond our horizon was seeded by the same quantum process. The same inflation that produced the fluctuations in our observable universe produced fluctuations throughout the inflated space. The same random quantum noise. The same statistical distribution. The same process. But different specific outcomes, because quantum mechanics is inherently random. The large-scale structure beyond our horizon is similar in statistical character to our own. It has the same kinds of filaments, the same kinds of voids, the same statistical fingerprint of inflation. But the specific configuration is different because the random quantum draw was different. Our observable universe is one realization of a statistical process that played out across a vastly larger space. The beyond contains the other realizations. All the other draws from the same quantum probability distribution. Different positions for galaxies. Different sizes for voids. The same underlying rules. The same physics. But different outcomes, as different as any two hands drawn from the same shuffled deck. This means the beyond is simultaneously similar to our universe and different from it. Similar in its rules. Different in its specifics. A vast space of variation built on the same foundation. There's a final thing worth understanding about what lies beyond the observable universe. Something that rarely comes up in popular discussions because it's deeply uncomfortable. We have a preferred position in time, not space. There's nothing special about where Earth is in the universe. We're on an ordinary planet orbiting an ordinary star in an ordinary galaxy. Nothing about our spatial position is privileged. But our position in time may be privileged in a specific sense. We live in an epoch when the cosmic microwave background is detectable, when galaxy redshifts can be measured, when the expansion of the universe is observable, when the large-scale structure of the cosmos is visible. In the far future, all of that evidence will be gone. Galaxies will have receded beyond our event horizon. The cosmic microwave background will be stretched to unmeasurable wavelengths. The redshift data will be inaccessible. Astronomers in the very far future, if they exist, will have no way to deduce that we once had access to all this evidence. They'll be in a universe that appears static, local, and eternal. They will not know about the Big Bang. They will not know about the expansion. They will not know about the multiverse, or inflation, or the cosmic microwave background. All of it will be gone, erased by the very expansion that we currently use as evidence. This means we live in a cosmologically privileged epoch, not spatially privileged, but temporally. A window of cosmic history in which the evidence of our origins is still accessible. The window will close. Not in any human timescale, but in the grand timescale of the universe. We are at a moment where the cosmos is still readable. And we are, perhaps for the first time in our history, reading it. Trying to extract everything we can from the evidence before it's gone. The question of what lies beyond the observable universe is not just an abstract puzzle. It's urgent, in the deepest sense. This is the moment when the answer is most accessible. This is the moment when the tools are powerful enough to probe inflation, to search for bubble collision signatures, to map the acoustic oscillations in ancient light. If we're going to find evidence of the beyond, it will be in these decades, these centuries. Not in 1 trillion years, when the evidence is gone. The universe is most knowable right now. And we happen to be the species that exists right now, asking the question, that is a remarkable coincidence. Or perhaps not a coincidence at all. The universe started small and hot and dense. It has been expanding for nearly 14 billion years. Everything we know is inside a sphere defined by how far light has had time to travel. Beyond that sphere, there is almost certainly more universe, with the same structure and the same laws, extending for distances that make our observable region look like a mote of dust. Beyond that, if inflation is correct, there is an eternal ocean of expanding space, punctuated by pocket universes where inflation has ended, each one a cosmos unto itself, with possibly different physical laws. And if quantum mechanics means what its most literal interpretation says, then alongside every branch of every quantum event, there are other histories, other versions of this moment, undetectable but real. The question of what lies beyond the observable universe doesn't have a single clean answer. It has layers. Each layer is less certain than the one inside it. Each layer is supported by a combination of theory and evidence that becomes more indirect the further out you go. But none of it is nothing. The cosmos is indifferent to the limits of our detection. Whatever is out there, it is out there right now, existing, evolving, following whatever laws apply to it, completely unaware of us and our cosmology and our careful attempts to reason about what it must be like. And we are here, doing exactly that. Reasoning, building theories, pushing the mathematics, looking for signatures in ancient light, trying, with the limited tools of a young species on one small planet, to understand the structure of everything. The fact that we've gotten as far as we have is, in its own way, as remarkable as anything we've described tonight. The next time you look at a clear sky and see the stars sharp and still against the dark, remember that what you're looking at is a window into a distance that has a hard limit. Beyond the furthest star you can see, beyond the furthest galaxy any telescope has imaged, beyond the cosmic microwave background itself, there is more. We don't know exactly how much more. We don't know what form it takes in its furthest extremes. But we have looked as hard as physics allows. We have followed the reasoning wherever it leads. And the answer it keeps giving us, in every model, in every calculation, from every direction of inquiry, is the same. More. Always more. Good night.